My screen. All right. If I can find, perfect. Here it is. Are you able to see?
Yeah, that looks good. And we
Excellent.
can see your full screen. Go ahead.
Perfect. Thank you. Yes. So as mentioned, my name is Kacy Hatfield. I am currently a machine learning intern at NASA Goddard, as well as a PhD student at Arizona State. This work is a collaboration with Connor Nixon at Goddard and John Santerre at U Chicago, and it was recently published in JGR Planets on enhanced detection of Martian dust devils from rover images using machine learning. This talk is organized into four parts. First, why dust devil detection matters for Martian climate science. Second, the model and detection pipeline itself and the reasoning behind our architectural choices. Third, results from Jezero Crater and what the pipeline actually found when applied to Perseverance imagery. And fourth, directions for our future work. Dust devils are a primary mechanism for injecting dust into the Martian atmosphere. They influence surface albedo, atmospheric thermal structure, and are a direct input to general circulation models. Accurate climate modeling depends on constraining dust devil activity, location, frequency, and size. And without these reliable activity statistics, the dust budget in these models is poorly constrained. The rover NavCams provide a systematic ground level record of this activity. So this is the data we chose to exploit for this machine learning purpose. Several factors compound to make this object detection problem difficult. Manual inspection is time-consuming, subjective, and it doesn't scale to modern image archive volumes. Dust devils are low opacity and amorphous, so compression artifacts during transmission frequently obscure already faint features. As you can see in this spirit image, the dust devil is in the center and it's pretty faint. This is full resolution, so you can imagine as it becomes more compressed, it becomes more and more difficult to see and distinguish from background terrain. Orbital methods, while useful, only identify dust devils that leave surface tracks or are visible from orbit, and therefore they miss a substantial fraction of total activity. We needed an approach that's sensitive to motion signatures and adapted to visually ambiguous targets rather than one optimized for well-defined high contrast objects. We chose to use faster RCNN as our base model ready for modification for several specific reasons, each addressing a constraint particular to this problem. The first reason being COCO pre-training. Before we ever show the model a single Martian image, it was already trained on COCO, which stands for Common Objects in Context, and it's a large public data set of everyday photographs like you see on the bottom left. It's used widely to teach a model basic visual building blocks like edges, textures, and gradients. And since we have so few labeled Martian dust devil examples, we can't teach the model those basic visual building blocks from scratch. So COCO pre-training gives the model that foundational vocabulary in advance, and it transfers reasonably well, even to a domain as different as Mars. Second, the architecture itself is simple, low compute, and reproducible, which matters for the proof of concept study, where understanding why the model was making a particular decision was more important to us than squeezing out maximum raw performance. Third, we use bounding boxes rather than pixel level segmentation because dust devils are diffuse and semi-transparent, so they don't have a well-defined edge to begin with, and demanding a pixel precise outline would impose a level of precision that we were unable to support. So a bounding box was the right level of commitment given what was actually visible. And lastly, a faster RCNN architecture has a region proposal network. This diagram walks through how it works. So initially, an anchor grid is overlaid on top of an input image. As you can see, that input image does contain a dust devil. And the network scores each region for how likely it is to contain something within the class of interest. In our case, the class was dust devil. From there, it proposes a dense set of overlapping candidate regions to the highest scoring areas, and those candidates get refined to a single final proposal, which is the bounding box you see on the right labeled dust devil. The key is that this doesn't require fine detail, only coarse spatial structure, which suits a target like dust devils, which don't have sharp, consistent edges and textures to lock onto. Before we show results, it's worth being precise about what we're measuring and what metrics we're using to do so. Here's a dust devil, and here's a ground truth box, the true extent of the detection as determined by the annotator. Now, hypothetically, here's what our model would predict in yellow. Notice it doesn't line up exactly with the ground truth. It's offset and a different size, which is a normal case and not the exception for a target so diffuse. To score how good this prediction is, we look at two areas: the intersection where the two boxes overlap and the total area covered by either box. The ratio of this intersection to union is referred to as IOU, and it gives us a single number between 0 and 1 that captures how well the prediction matches reality. 0 being no overlap at all, and 1 being perfect overlap. In practice, neither of these extremes is typical, and so we usually see a partial overlap, what's shown here, or somewhere in between. This number is what lets us draw a line and say the detection counts as correct. For example, hypothetically, this covers roughly 70% of the ground truth box. The predict box covers 75%. So at AP 75, this would be considered a true detection. However, at AP 90, that would require the predicted box to cover 90% of the ground truth box, and this detection would be considered incorrect. Before modifying or fine-tuning our own model, we took 3 standard object detectors right off the shelf with no Mars-specific modification. So faster RCNN with 2 different backbones, ResNet 50 and ResNet 101, and the backbone being the part of the network that extracts visual features. And then we also evaluated RetinaNet. At average precision, or AP, across all thresholds was near 0. And to us, this was attributed to a fundamental visual mismatch, since dust devils are non-rigid, low opacity phenomena with gradual intensity gradients, and COCO objects are typically solid, well-defined, and high contrast. Fine-tuning on domain-specific imagery is therefore not merely beneficial for our case, but necessary. Our dataset spans 3 rovers over a range of terrain, lighting, and mission conditions, which was intended to support generalization across environments rather than overfitting to a single surface type or illumination environment. We used a scene-based splitting to construct terrain validation and test sets. A scene here being a single continuous span of frames captured at one rover location at one time. So for example, at the top of the valid set, you see this mountainous terrain. Any image that had that same geometry of mountainous terrain would be sorted into the valid set. The result split ratio was 68% train, 19% validation, and 13% test. This table documents the scene to split mapping in full. The rationale was straightforward. If images from a single scene appeared in both training and testing sets, the model could exploit background similarity that was unrelated to dust devil presence and inflate apparent performance without genuine generalization. Scene-based splitting ensures evaluation occurs on environments the model has not encountered during training. So to go over the complete overview of our fine-tuned pipeline, the NavCam frames pass through a random forest pre-filter for candidate selection, and then proceed along 2 parallel paths, raw frames and difference enhanced frames, each processed by a fine-tuned faster RCNN. Detections from both paths are fused using a weighted non-maximum suppression, weighted 70% towards difference enhanced and 30% towards raw, depending on whatever carried the stronger signal during validation. And the final result is a detection with associated metadata. The darker components are novel contributions. Both faster RCNNs are heavily modified and fine-tuned, and the NavCam frames were taken as is. I'll dive further into our contributions, starting with the random forest pre-filter. A substantial fraction of rover imagery does not contain dust devils or scenes that are possibly containing dust devils. For example, close-up shots of terrain, rover hardware, or sky-only frames, as you see on the left. Passing all such frames through the neural network is computationally unnecessary. The random forest classifier is a simpler, much faster model than the deep neural network used for the detection itself. It uses features like sky ratio, surface texture, and the presence of rover hardware to discard frames that are unlikely to contain dust devils before they reach the detector at all. This reduces computational cost prior to deep learning inference, which is relevant for both current processing efficiency and onboard deployment. Moving forward to frame differencing, this step is where planetary science methodology most directly shaped our pipeline architecture. Dust devils exhibit motion across consecutive frames, and static background terrain does not. We therefore were able to compute the absolute difference between sequential frames' pixel values. So we used previous, current, and next frames. And this amplifies regions of temporal change, and it suppresses static content. In the raw frame seen at the top, the dust devil is difficult to distinguish from the background terrain, even though this is one of our strongest examples. And it's even more difficult if you look at a single image without the sequential. In the difference image, however, the motion signature is clearly visible. This enhanced signal is what the model is trained to detect. This technique is not adapted from computer vision or machine learning. It's derived directly from manual frame comparison methods long used in planetary atmospheric science to identify vortex activity in rover image sequences. We formalized an existing observational practice as a pre-processing step within our detection architecture. Here again are the off-the-shelf baseline results for inference, which is near zero performance on all AP metrics. When you compare that to our model, shown in red, it's clear our model performs substantially differently. The metric most worth focusing on is AP50. Recall from a moment ago that this is the 50% IOU threshold, which is an appropriate lenient, if not strict bar, given that a dust devil is non-rigid and diffuse. So demanding near perfect overlap the way you would with a dog or a car with fixed edges doesn't make sense for a target that doesn't have fixed edges to begin with. By that standard, our model is expected to behave as it does, given how demanding that overlap standard is for a diffuse target. This improvement is attributable entirely to domain-specific fine-tuning on a modest dataset using standard architecture. Model complexity was not the limiting factor, domain adaptation was. We then applied our finished pipeline to Perseverance NavCam imagery from sols 1 through 200, a portion of the archive that to our knowledge had not been previously subject to a comprehensive dust devil search. The pipeline identified 19 unique dust devil events across 73 frames, and 18 of these were previously unreported, although one corresponded with a dust devil that was noted in a Flickr post by an amateur astronomer, which was a nice internal check that the pipeline could recover a known event in addition to surfacing new ones. This detection from Sol 76 illustrates one of our strongest dust devils. It is most visually apparent without difference imaging, and you can see ingenuity in the frame moving as the GIF progresses. It's worth noting that even though ingenuity is a dynamic object in frame, it was not considered by the detector as a dust devil. This is from Sol 102, and it shows how our confidence metric output by the model tells us how confident the model is that within the rectangle that it outputs, there is a dust devil contained in there. One of our biggest caveats is the imaging bias we incurred. The top panel shows all NavCam observations across sols 1 through 200, and the bottom panel shows temporal distributions of our 19 detections by mean local solar time. The detection cluster is in the morning and there's a drop off after 11:30. Imaging frequency is also highest during this window, so the observed pattern is confounded by acquisition bias rather than reflecting atmospheric behavior. What this analysis does support is that detection is strong within the observed window, but whether comparable activity occurs in the afternoon remains an open question that this dataset, given its imaging bias, cannot resolve. For a subset of detections with stereo NavCam coverage, meaning that the same dust devil was captured in both the left and right NavCam at the same time, that same feature or dust devil appears at different horizontal pixel positions in the left and right images. This disparity, combined with the known camera baseline or the distance between the two camera sensors, allows distance from rover to dust devil to be recovered through standard stereo photogrammetry. Combined with bounding box height in the image space, this yields a physical estimate of both distance from rover to dust devil and dust devil height. Measurements like this can be used directly for climate model validation or frequency analysis, rather than remaining purely pixel-based quantities that are ungrounded. This faster RCNN architecture presented here is explicitly a proof of concept rather than a finished system. The next architectural step is mask-based segmentation, which would provide pixel-level delineation of vortex morphology and opacity. This requires more extensive annotation than bounding boxes, and it was deliberately deferred rather than pursued initially. Beyond that, we intend to scale the pipeline to the full Perseverance archive and subsequently to the other Martian rovers. In parallel with that scaling effort, three things are worth highlighting. building towards a systematic catalog suitable for size frequency analysis and validating general circulation models and other machine learning models. Recovering physical size for 19 of the 16 of the 19 detections that lacked stereo coverage, which would require monocular depth estimation adapted for Martian terrain, and longer term onboard prioritization utilizing the machine learning model's capability of predictive behavior, flagging atmospheric events in real time so they can be retained at higher resolution or prioritized for downlink on future missions. In summary, fine-tuning an object detector for Martian dust level detection, combined with our planetary science-based pre-processing, established a pipeline capable of identifying novel events and providing measurements necessary for further dust level analysis. Our data is available on Zenodo as with our code. This QR code leads to our GitHub repository, also with our code and data. I appreciate you listening to this talk, and I'm happy to answer any questions. Thank you.